Hi, my name is Lorenzo Nicora and I am Streaming Solution Architect at AWS, and I would like to introduce you to some of the fundamental concepts of stream processing. In this video, we will see what is streaming and why we need to process data in streaming, how to do it, and how to implement business logic that is based on the when, or what are called time semantics. And in the journey, I will keep comparing streaming with more traditional approaches. But let's start from the definition. What is streaming? In the context of data streaming, the terms usually refer to two separate meanings. The first is to describe the nature of the data, what we process, and the second to describe the processing mode, how we process it. When referring to the nature of the data, streaming implies unbounded datasets, virtually infinite stream of data that we can only observe partially. In contrast, a bounded dataset, like a table or a relation, can be big but is finite, and we can observe it completely. When referring to the processing mode, streaming implies processing data continuously. Data points are processed as they arrive. In contrast, again, when we process data as batches or periodically, we process a big but finite bulk of data one at a time and in a finite time. Processing is often scheduled but not necessarily. A bounded dataset, a table, often represents a snapshot of the state of the system at a given point in time. The content of the table may change over time, of course, but at the given time we can know it completely. Conversely, an unbounded dataset or a stream is a sequence of discrete messages or events. Stock transactions in this example. Each event is independent from the others, and each event usually has a timestamp representing when the business fact has happened, the transaction execution time in this case. But why should we process data continuously in streaming? One of the reasons is to process data continuously is to reduce the latency of the result. And with latency, in this case, we refer to the delay between when the actual event has happened or when we ingest it in our system to the moment we can provide the result of our calculation or our analysis so we can act on the basis of that. And the point is the value of the data and the value of the insight diminishes over time. And we are talking about business value, but it can also be direct monetary value. And this value can also become negative, a loss, as you can easily imagine in the case of fraud detection. But let's see a couple of example use cases that I will use during this presentation. The first is IoT telemetry. Imagine we have a fleet of industrial motors across multiple plants. To work safely, motors must run within an operational envelope that can be defined in terms of speed and temperature. Occasionally, motors can overheat or speed too fast or too slow, getting damaged. So we have installed a network of sensors on the motors, and sensors continuously sample speed and temperature and send them over a mobile network to a central control system. Our goal is to minimize the risk of failure and to reduce the maintenance cost. A completely different use case is a trading platform offering intraday trading to professional traders. Each trader buys and sells stocks many times a day, sometimes many times every hour or every few minutes. One problem for traders is to monitor their exposure to certain stocks or asset classes or markets. And they also want to monitor the profit and loss of their strategy. As a trading platform provider, we want to build a customer-facing analytic platform to allow our customers, the traders, to monitor and improve their strategy. From a latency point of view, let's see what happens when we process data in batches or periodically. Well, the event is generated at time 1, and this is the moment the measurement is made by the sensor or the stroke trade is executed. And our system ingests the event at time 2, so when our control system or analytical platform receive the data point. And because we process data in batches, the batch will only start at time 3. The batch will take some time to run, and we will eventually emit the result set at time 4. Ignoring for the moment the time between when the event is generated and it is ingested, so between time 1 and time 2, because this is not under our control, we can say that the delay of the result from ingestion to the result being available, so time 2 to time 4, mainly depends on the period of that batch and the time it takes to process the batch. We can improve the latter, throwing more resources to the processing. And we can definitely shorten the period of the batching, but this is a heavy cost to latency trade-off. And we may end up with batches that start immediately one after the other, practically doing streaming with a tool that probably is not designed for it. It's interesting to observe that latency is variable in this case. It depends heavily on when the specific data point is ingested, at the beginning or closer to the end of the batch. So it varies between a minimum, that is the time it takes to process the entire data set in a batch, 5 minutes in this example, to the sum of the processing time plus the duration of the batch. So 65 minutes for a hourly batch. When processing data continuously, things are slightly different. We still have a time between the event is generated and the event being ingested, time 1 to time 2, and this is probably the same as in the previous case. But now processing starts almost immediately, and in this case latency depends only on the time it takes to process the data. And in this case our constraints and trade-offs are slightly different. Well, similarly to batching, processing time may also depend on the available resources, but this is often not the most important factor. The delay also and mainly depends on the type of logic we are applying, particularly aggregation. They are often based on time windows. Let's give a simple example. So if we want to calculate the average of some value every minute, we need to accumulate 1 minute of data before emitting the result. So our result will always be delayed of at least 1 minute. Let's get back to our use cases and see the practical effect of processing data in batches or in streaming. And please note that neither of these use cases is considered low latency or strictly real time. So for motor telemetry, if we process data every hour, this gives us the possibility of identifying the potentially damaged motors and then schedule maintenance to prevent a complete failure. But if we process data continuously, we can act as soon as we identify a motor at risk and then send a signal to stop the motor and prevent any damage. For our trading platform, if we provide our customer with an analysis every hour, this is probably better than most of our competitors are already doing. This will allow traders to analyze their strategy and the risk, but only post facto, only when things has already happened. In an hour, probably most of the position are already reopened or closed. They can learn for the future, of course. But if we process data continuously, we can send an update of the result on every trade or every few seconds. And this will allow traders to act preemptively, adjusting their position and their strategy on the flight. But this is not just about latency. In fact, the real world generates data continuously, not in batches. This is an unbounded flow of data, and this doesn't happen at fixed time. So our motors continue spinning and our sensor continues sampling the data. And every single trader will probably buy and sell stocks multiple times in an hour. When we receive data periodically, as it often happens, this is usually due to a limitation of some of the upstream systems we have, rather than the actual nature of our business being batchy. If the world generates data continuously, and we often process them as batches, how do we do it? Well, what we usually do is we split data in arbitrary fixed size windows, and we process each window of data one at a time periodically when the windows end. The size of the windows is usually determined by the period of the batch. So if we process data on every hour, we are processing 1 hour worth of data. At each round, we process the entire window of data, and for each batch, we produce a result that is often aggregated in a data store. When we process the same unbounded stream of data but in streaming mode continuously, we can actually do something very similar. A simple way of doing it is to split the infinite stream of data into finite windows at fixed time. At the end of each window, we generate result that is a stream itself. But this is just one of the possibilities we have, possibly the simplest. In stream processing, this is called processing time windows. We will get back to this in a minute or two. Let's see in more details the difference between processing bounded and unbounded datasets. With a table, a bounded dataset, we can process the entire dataset at once. A SQL query, for example, goes through the entire input set and produces a single dataset. This is also true for bigger data, let's say. If we're using a big data framework like MapReduce or any distributed query engine, what we are doing is parallelizing the processing, splitting across nodes, but we are still processing finite data sets in a single and finite run. With streaming, the process is completely different. Remember, our stream of data is infinite. We can never see all the data. We can visualize the process, a simple filtering query in this case. Imagine the query is moving through the stream, and the query processes data at the moment they become visible, the now of our system. And the query emits the result, the filtered stream in this example, as it scrolls through the input. But let's start with the simplest case of stream processing logic, time agnostic logic. It means logic that doesn't include time as a factor. The simplest example of time agnostic logic is filtering based on some property of the event. So let's imagine our sensor measurement, and we want to keep only the temperature measurement. Note that filtering is stateless. It means that we can process one event at a time without any knowledge of the event that came before or that will come after it. More complex logic can also be time agnostic. Inner join is an example. Imagine we have two streams of data, and each event in one stream matches exactly with one event in the other stream. An example of this can be an e-commerce platform where payments are collected asynchronously, and we produce the stream of orders and payments. Downstream, we want to enrich the orders with some information about the payments. And this is a simple inner join by order ID in SQL terms, and it will be the same in streaming terms. But remember, this is streaming. We process data continuously. We don't have a table, and we want to process data as soon as they arrive. But the problem is the two corresponding events will reach the component doing the inner join at different times. So what we need to do is buffering each event until the corresponding event on the other side is received. This kind of process is called stateful. It means that our system needs to remember some state, in this case just the event that comes first, to be able to calculate the result, the enriched event in this example. But let's see how it works with a simple animation. So the first order reaches our node doing the join, and we buffer it, or we keep it in state in the streaming jargon. Later we receive the second order and we keep it in state as well. At some point we receive the payment of the second order. We can match it, emit the result, and discard the match order from the state. Later on, we receive a third order and a payment related to the first order. We can match it, emit the result, and discard again the newly matched order from the state. Then we receive a new payment, and this time it doesn't match any of the orders we have received yet. Well, this is not a problem. We just keep it in state. We receive another payment. We can match and discard until we eventually receive the fourth order, matching the payment we received first. So we can match it and discard. So at this point, our state is temporarily empty until we receive the next order of payment. With a slightly different representation, we can imagine the join process scrolling through the two input streams, the stream of orders and payment, temporarily buffering the events that on the side that comes first until the corresponding event on the other side is received. And this process lays behind a stream of output, the order enriched with payment information. Note that this process is time agnostic, as we said, because the time the order was placed, the time the payment was collected, or the time we are doing the join do not matter. But differently from filtering, this process is stateful because we need to buffer the elements for some time. In reality, we actually need to have some form of garbage collection that is probably based on time, but this is not related to the logic. So what if the corresponding element on one side never arrives for any reason, for a failure, and we need to be prepared for failure? We cannot allow our state to grow unbounded. Otherwise, we may eventually run out of memory or disk space. And a garbage collector is often based on a simple timeout. So an unmatched element will be dropped after some time. That may be long, but it's finite. And expired event do not need to be lost, do not need to be ditched. They can be sent to a special output, to raise an alarm, or for some special handling. But more complex logic often has time as a factor. But the concept of time doesn't have a single definition. Let's see what are the different time semantics or time domain we can use. Let's revisit something we have seen, but from a different perspective, from the perspective of a single event. As we have seen, the event usually happens externally from our system. We call it the time when the event actually happens, event time, time one on this diagram. This is often written in the event itself by the source system. Then data takes some time to reach our system from the source. This can be millisecond, can be second, can be more, depending on our system. And sometimes it can vary over time, especially for heavily distributed system. The instant our system received the event is called ingestion time, time 2 in this diagram. And finally, we process the data. Processing can happen briefly after the ingestion, but let's consider it a different point in time. The instant we handle the processing of the event is called processing time, time 3 in this diagram. The most relevant time we use are usually event time and processing time. And we can talk about event time semantics or event time domain and processing time semantics and processing time domain. This chart represents the relation between event time and processing time. In an ideal world, represented by the dashed white line, where information propagate instantaneously, processing time would always be identical to event time. Unfortunately, in the real world, represented by the orange line, source systems are distant. At the minimum, we are limited by the speed of light, but usually data propagates slower than that. And propagation time may vary over time due to congestion of the network, failure, system being disconnected, etc. So the one important observation is processing time is always different and later, of course, of event time. And this difference between the two varies over time. And usually there is no simple correlation between the two. There are many use cases where we are actually interested in when the event has happened. So, for example, when we are talking about financial transaction, we're interested when the transaction was executed, rather than when we receive the corresponding data. And this is not just finance. So, for example, if we need to correlate events coming from different devices, especially if the data are delivered over mobile network that can be temporarily disconnected, we probably need to use event time for the correlation. But we saw in real world there is no fixed correlation between processing time and event time. It means that we can't use processing time as a proxy for event time. And we cannot use processing time as a way of representing in any way event time safely. The implication is, for these use cases, our processing system, our framework, must support event sign semantics. What does it mean? It means that we can implement logic based on when the event has happened, based on the time that is written in the event itself by the source, the transaction execution time, for example, rather than the current system time when we are doing the processing. Now we understand the difference between processing time and event time. Let's see some example of logic that do depend on time. A typical example of non-time agnostic logic is windowing by time, means slicing data in time-based windows. So, for example, to calculate the average of a measurement over 5 minutes. The simplest case we have already mentioned is processing time windowing. So windows in processing time domain. So windows are based on the current time of the system, or wall clock time, as is sometimes called. Imagine you set up a timer when you open the window. When the timer expires, you close the window, you calculate the result, and you open the next window and restart the timer. Processing time logic is useful every time you need to do some calculation, some analysis based on when the event is observed, not when it actually happened. An example of this can be a media broadcasting service, and they want to scale their infrastructure dynamically based on the number of viewers. And they decided that a good metric for that is scaling based on the number of viewers of the last 10 minutes. Video devices are regularly emitting signals when the user is watching. We do not care about the delay of propagation of this signal, also because probably the video stream is affected by the same lag too. We need to decide whether to scale our infrastructure based on the number of devices that have been connected in the last 10 minutes. And connected means we have received a signal or we observed it in the last 10 minutes. So this is clearly processing time logic. We have already seen how processing time windows works in a streaming engine. Similarly to inner join, we need to buffer data. It means that this process is stateful. But differently from inner join, in this case, we buffer events exactly for the duration of the window. In our example, because we need to calculate the average of viewers over 10 minutes, we accumulate data for 10 minutes, we calculate the average, we emit the result, we ditch the events, and we start a new window. Also note that there is no problem of completeness. When do we have the result of the full window? It's simple when our timer expires, when our current time passes the end of a 10-minute window. Any signal coming later of this limit will just belong to the next window. There is no risk of an event coming in late. But windowing also makes a lot of sense in event time. Actually, we often aggregate data based on when the event has happened, not when we observe it. But here, a new problem arises. We saw that processing time is not a good proxy for event time, but our windows must be based on event time, so what is written in the event themselves rather than the wall clock time, our timer. Problem is, we don't know exactly the delay between when the event happened and when we process it. But also often, events have the bad habit of arriving out of order in respect of event time, especially if they're coming from different sources. So we need to buffer events to give them time to arrive and have the ability to reorder them. But how long? So how do we solve the problem of out of order events and completeness when working in event time domain? How do we decide when all events belonging to a specific windows have actually arrived? And we need to wait for them before calculating the result. Also remember, windows are based on event time too, and events may arrive out of order. So what timestamp can we use to decide when to open and close the window? And also, how long should we wait before closing the window to allow some out of order, particularly late events to get in? The reality is there is no simple answer. One possible approach to this problem is using watermarks. This is the approach used by the Dataflow model and by Apache Flink, an open source implementation of this model. Each watermark refers to a time, in event time domain, of course. A watermark is literally a simple message saying this is the watermark for time t. And these messages are injected in the data flow with the other events. Any event time logic, so for example deciding when to open or close a window, is based on the watermarks, not the timestamp that are written in the event themselves. And each watermark represents a logical barrier saying after this watermark there is no event with event time older than me. So for example, when you receive the watermark with the time that is greater than the window end time, you can close the window. Watermarks also provides a clear semantic for the time horizon of the output, our result. So when a watermark reaches the end of the flow, we know that no data that were more recent than the watermark has been included in the result. If we have a perfect knowledge of our input data, we can implement perfect watermarks. It means that no late events can happen. No event older than the watermark time will happen after the watermark. In the real world, we seldom have a perfect knowledge of our inputs, and data can be delayed due to unexpected congestion, failures, disconnected devices, all conditions that are external to our system and we cannot control. In this case, we need to use a heuristic watermark, an approximate watermark. One way of implementing a heuristic watermark is to take the most recent event time we observed so far, and then we add some margin of error, for example, an expected maximum lateness. This will become our watermark time, and we can inject watermark messages in the flow periodically. These watermarks will not be perfect, but also they are a compromise between latency and completeness. If we give a shorter margin for late events to come in, we reduce the latency of the output. But if we give a longer margin, we reduce the chances of messages coming late, but we are increasing the latency of the output. When a watermark is heuristic, it means that it can happen that events that are older than the watermark actually arrived after the watermark itself. You can see, for example, in the picture, the event with time 18 has actually arrived after the watermark at time 20. And these are called late events. And you must handle them explicitly. The good news is that almost every modern stream processing framework allows you to handle late events explicitly as first-class citizen of the programming model. And you usually have three options. The simplest is discarding late events. This is good when all data are no longer relevant. This is probably good if you are handling measurement, for example. This is definitely not good if you are handling financial transactions. Another option would be updating the result and emitting an update of the result itself, so our destination can handle it and update its own internal state. This will require some additional buffering, and also the destination system must be ready to accept this kind of late updates. A third option would be sending late events as they are to a secondary output for some special external handling. This can be simply raising an alarm or some manual handling. Which option to use and the actual implementation completely depends on the business use case. And please note that these problems of completeness and late events are totally not unique to stream processing, even though we tend to forget them when we are building a batch implementation. Let's see an example. We have a daily batch that must process all transactions that have happened during the day. So this is event time processing. The batch runs at fixed time, as a cron job, for example, and this is processing time. We are practically implementing event time logic and using processing time windows. And you can probably start seeing what is the problem here. We need to wait for all transactions of the day to be ingested before starting the process. So we decide that we run the batch later than midnight, let's say an hour. Note that this is very similar to establishing a heuristic watermark with max lateness of 1 hour. But in this case, we are kind of mixing event time and processing time domains. Most of the time, we are lucky, and all transactions are actually ingested before 1 a.m. But once we are not so lucky, maybe due to a temporary failure of one of the upstream systems sending us transaction, something we do not really control. So some transaction actually arrived after 1 a.m. And so what we do? First thing, we need to be able to detect these late events. And it means that we need to be aware it can happen, and our implementation should detect them explicitly. Then we need to include them in our calculation. A naive implementation may be just stopping batch and relaunching it, including the recently arrived events. But this will delay the entire results, possibly for very long, and possibly generating a lot of duplicates, depending on the implementation, of course. Sometimes we need to implement something smart, obviously. But this will add complexity. Also because the tool we are using doesn't really support this. So we need to invent something to handle this kind of special case. With streaming, these are not special case at all. We can explicitly define a heuristic watermark with a max lateness, 1 hour for example, and our framework will detect late events for us. The only thing we need to do is then decide what to do with these late events. So for example, being transaction, we can discard them. We can decide whether we can emit updated results or just send them to a separate output for an external handling. But let's conclude with some few more examples of windowing. There are some interesting use cases that require dynamic windowing based on event time. A typical example is clickstream analysis. So imagine we have a website and we want to measure the duration of each user session and the number of pages that each user visits during the session. A user session is defined as a sequence of interactions or click by a single user with pauses that are shorter than a given timeout, say 5 minutes. So these are defined as session windows with session timeouts of 5 minutes. Consider that session must be based on the time the interaction has happened. So this is clearly event time processing. And so we are talking here about session windows in event time domain. Imagine we have no strict latency business requirement here. So we are processing the website logs, and we can process the logs file once they are closed and rotated. And there is no need for you using stream processing just for the sake of latency here. So we decide to process logs as batches. On every hour, for example, we run a batch processing the logs that were rotated in the previous hour. But we can also trigger the process when each file is rotated. This will not make any difference, to be honest. The problem is batching works very well with fixed windows. But when windows are dynamic, and especially when windows can span across batches, this is much more complicated. And in this case, each user has independent sessions. And you cannot decide whether a session is finished or not until you wait for the future and you do not receive any more clicks. So this is not ideal and will introduce a lot of complexity. And the reason is each batch cannot process its own window of data as a finite data set. It also has to know what has happened before and what will happen after it. With a stream processing engine, we can probably ingest the files as soon as they are rotated, and from this point on, they become a stream of click events. So our framework can create session windows on the fly. A new window is open when a new interaction from a user is detected and is closed when no interaction happened after the timeout we defined. Most of stream processing framework like Apache Flink provide session windows out of the box. You just need to define the identifier of the user, so identify what is a unique user, the session timeout, and then implement the logic to process the click that belong to the session. The framework will take care of detecting the beginning at the end of the window and just calling your implementation every time a window closes. Getting back to fixed windows, what we have seen so far are actually called tumbling windows. This is because windows are kind of tumbling forward when they finish, and the next windows always starts immediately after the previous windows. This type of window is quite easy to implement with batching too, as long as the windows coincide or are completely contained in one batch. But there is another commonly used type of fixed window. They are called sliding windows. They're called sliding because each consecutive window actually slides forward of a fixed amount of time called window slide. And the slide is often shorter than the window size, so actually windows will overlap and events may belong to multiple windows at the same time. In this animation, the window slide is exactly half the window size, but this is just an example. It can be anything. Actually, it's often much shorter than the window size. So, but how can we use this kind of window? These are actually very useful. And an example of use of sliding windows is anomaly detection. Imagine imagine your stream of sensor data from the motors, for example. Situation where some of the operating parameters vary very quickly are considered dangerous. So what you can do is calculating the standard deviation of temperature or of the speed of the motor over a sliding window of say 5 minutes. When the standard deviation crosses a certain threshold, this can be considered an anomaly. So you can trigger an alarm and send the message and shut down the motor. With batching, sliding window will inevitably cross the boundary of the batch. And as we saw, this will increase the complexity because in this case we need to carry over data across batches. While in streaming framework, sliding windows will be directly supported by the programming abstraction. And we reached the end of our journey. Let's recap what we have seen so far. We have seen that when we talk about streaming, we actually refer to two different meanings. The nature of the data as unbounded datasets and the processing mode as processing data continuously. We saw the impact on latency of processing data periodically as opposed to continuously. And we saw the difference between processing in batches or in stream, an unbounded stream of data that comes in from the external systems. We saw why some processes require state and the difference between implementing event time semantics and processing time semantics. We also saw how to solve the problem of out of order and completeness when working in event time domain using a watermark. Problems that do exist also when we implement a batch. And finally, we saw various examples of windowing, both in processing time and event time. And we saw how sometimes it can be easier to implement some type of windowing with the streaming framework because it supports them out of the box. So thank you. I hope you find this useful. If you have any question, don't hesitate to reach out. And goodbye.